Okay, in this workshop we're going to create our own method. We're going to be based on the ideal method, and eventually we want to create one for activity and one for equation of state. Now methods, add ideal, then Robinson, and RTL. Okay, just add water, ethanol for example, but we are not going to use them. Now let's go to specification. You should have these three right here. Actually, what I'm going to do is create a new one. Let's call it method 1. And as you can see, this will be the worst case scenario in which we need to actually start from zero at all pure thermodynamics, mixture thermodynamic properties, pure transport properties, and mixture transport properties. We're not going to do that. We are going to base our method on the ideal one. And it will have a set of parameters already present here. So what we're going to do is try to set several components to those of NRTL and Penn-Robinson. So let's try to use all the relevant data on thermodynamics as activity model. So let's go here, NRTL, pure thermodynamic, Phi00. So let me take a copy of pure. So we have a reference. Okay, so let's go back to our process. Compare this. Okay, we are calculating phi equally. Actually, it's pretty similar to SO2. So the first thing it changes is this one right here. SO2. This one is 0, 0. Okay, but we're not using solid, so no worries. We don't need to change that. And what else? This one right here as well. Hydrocarbon solubility. And actually it's pretty similar to that of the ideal. Let's compare with Penn-Robinson. So this is a good exercise because you can now relate which properties are similar and which are not. So let's go back to our pure properties of our ideal model. And the first thing you will see is that these are different, 9 and 11. Let's verify what's that. This uses the standard Penn-Robinson equation of state model, and currently we are using ideal gas model. So that will be cool if we can calculate using this for the vapor and 11 for the liquid. This one. So what we are doing here is adding parameters to the phi equation. Remember that the phi, or the coefficient, is based on an ideal gas. Right now we're going to base it on Penn-Robinson. Let's see what else we can do. HV is based on 0.9. Once again, the standard Penn-Robinson model will be cool if we change that as well. Currently is using ideal gas with Watson model. And let's change it to 12. So you can do this as well. I'm not going to do all this, but the idea is to eventually you're going to find the gamma or activity coefficients, pure transport. Let's see how it goes. How are we going to pure transport? Calculate pure transport. Let me copy that and paste it here. Pure transport. So as you can see, pure transport has a difference here. It uses the steel totals, whereas we are using this equation right now. You could change it. I wouldn't recommend so. So actually, as you can see, For pure thermodynamic and transport properties, there is no huge of a deal. The actual huge deals are in the mixture thermodynamics. Okay, let me copy, paste this Penn Robinson, and this will be, sorry, let me open a new one so we can have reference. So this is NRTL, and this is Penn Robinson. Okay, let's verify mixtures. So initially you can see from the beginning that Penn Robinson uses this one right here, which is the vapor fugacity calculating using the Penn Robinson instead of ideal gas model. So I could say definitely if you choose this one, this will be better model because it uses parameters more extensive than the ideal gas. The same should be true for these two guys. So this one right here, the solid, well, solid is the same for us. I would say only that you should change, in my opinion. Oops, sorry here. These guys right here, this one was Phoebe. $38 and okay, and this should be, wait for it, $38, and the liquid one is 104. So here, that will be a good start for our model. The idea will be to test them, see which one gives the best result, and of course compare it with our experimental data. Now we have this model, always save it because you will need it on further workshops. So what we did is essentially, based on the ideal model, get the best of the NRTL and best of Penn Robinson equations, and assume that these will be relevant for our workshop. Of course, we need to test it with data, not because we add more complex equations means that we are going to model real-life equations.